Welcome back. You know, if I were strong enough to pull on this piece of steel wire until it failed in tension, the force I would need to apply would be about 150 pounds. Yet if I load the same wire in compression, it buckles at less than 1/4 pound. As a general rule, a tension member can be significantly lighter and more slender than a compression member, even if the magnitude of the internal force is the same in both cases, because compression members buckle and tension members don't. We can see this phenomenon manifested in many great structures. In Brunel's Royal Albert Bridge, for example, the magnitude of the compression force in those top chords is about the same as the magnitude of the tension force in the bottom chords. Yet the top chords are huge iron tubes, while the bottom chords are visibly lighter eye-bar chains. Wouldn't it be wonderful then if we could build structures in which all of the principal load-carrying elements were in tension? Those structures would be exceptionally light and efficient, capable of spanning long distances and enclosing large areas. The use of slender, flexible tension elements would also open up all sorts of new possibilities for architectural expression. Well, as you've probably guessed, we can build structures in which all of the principal load-carrying elements are in tension. Logically enough, they're called tension structures. And because the principal load-carrying elements in these structures are usually steel cables, they're sometimes called cable structures as well. Sometimes the cables are integrated with a thin, flexible synthetic fabric called a membrane. The roof over the Denver International Airport is a typical example, one we'll revisit later in this lecture. The metal cable is actually a relatively recent technology. Recall that the world's first permanent wire cable suspension bridge was built in 1823, and twisted iron wire rope was probably invented somewhere around the 1830s. So the tension structure is a distinctly modern structural configuration. However, there is one ancient antecedent. The Roman Colosseum's rope and canvas awning, called the velarium, which we'll also revisit shortly. Now, as you've probably noticed, today's lecture is really just an extension of our previous lecture on long-span roofs. Tension structures are most often used for the roofs of sporting arenas, entertainment facilities, transportation terminals, and similar large public buildings. I'm addressing tension structures here as a separate lecture, in part because I find them so fascinating, and I hope you will too. But more importantly, tension structures provide us with unique opportunities to apply the concepts we've learned elsewhere in this course in new and exciting ways. A structural element can carry tension in only one way, through internal force directed along the axis of the element. For this reason, load paths are very evident in tension structures, and the principle of equilibrium is often beautifully illustrated at the points where the various structural elements are joined together. In preparing this lecture, I was actually kind of disappointed to find that there aren't many good photographs of the world's great tension structures. And the photos that are available don't really adequately depict how these structural systems work. As such, I'll be relying heavily on physical models to help us see and understand these unique structures. So let's begin with the world's first building to use a cable-supported roof, the J.S. Dorton Arena in Raleigh, North Carolina. This building was originally the Raleigh Livestock Arena. It was developed for the North Carolina State Fair, and so, predictably, it's been nicknamed the Cow Palace. The arena was designed in 1950 by a Polish architect named Matthew Nowicki. Sadly, Nowicki was killed in an airplane crash that year, and a Norwegian-born engineer named Fred Severud was called in to complete the work. Severud proved to be more than up to the task. Indeed, he went on to become one of America's great pioneers in tension structure design. The Dorton Arena was completed in 1952. The floor area enclosed by this building measures 221 feet by 127 feet, and it can accommodate up to 7,600 people. This photo doesn't really do it justice, though, so let's build a model. Here's a model of the basic framework of the Dorton Arena, and that basic framework is composed of a structural system that's founded on two huge reinforced concrete arches. The arches are each parabolic in shape, but in the actual structure, as you can see here, they're inclined on a sharp angle in opposite directions, intersecting about 26 feet above the ground. The roof then is suspended from these two intersecting arches, and it's developed in the form of two sets of intersecting steel cables. I'd like to add to our model by adding representations of those two sets of steel cables. And the first set I'll add, I'm going to use yellow thread to emphasize it as distinct from the other set. This first set of cables stretches from arch to arch. So I'll begin out here, and we'll run the cable across to the opposite arch, and then across again in the opposite direction, parallel to the first, and so on. Now, one of the great advantages of this sort of means of construction is that in the actual structure, it can be done quite rapidly. And that completes the first set of cables. Now we'll add the second set. In this case, we're going to run across each arch from side to side. So we'll begin out here, and if you'll allow me to very quickly finish stringing this set of cables. And now our model of the world's first tension roof structure is complete. In order to actually complete the roof of the real structure now, once the steel cables were in place, a lightweight cladding of steel sheeting was added over the top with a steel panel located over each one of these rectangular grids. The result of the network of cables moving in both directions is a saddle shape. In fact, it looks very much like a high-par thin shell roof, as we covered a couple of lectures ago. However, this is not a thin shell structure. It's not a thin shell because it's acting principally in tension rather than in compression, and the roof itself is not a continuum in the way a thin shell concrete structure is a continuum made of monolithic concrete. Now, what's really fascinating about this structural system is that in addition to the obvious fact that the arches support the roof also supports the arches. The cables spanning from arch to arch are actually holding up the inclined arches. I think you can see that without the cables in place, there's a tendency for the arches to fall outward. So once the cables are in place, they significantly stabilize the structural system. And similarly, the cables spanning across each individual arch, the pink cables in my model, serve to help restrain the lateral thrust of the arches in order to improve their strength and stability. In fact, the structural system of the Dorton Arena is actually very similar to a common director's chair, which uses the tension in the fabric seat to hold up the chair, just as the Dorton Arena's cable roof structure helps hold up the arches. Now, at this point, I should explain something that you've probably already noticed in the model. The cable roof of the Dorton Arena carries load entirely in tension. It's a tension structure. But the structural system as a whole actually includes some critically important compression elements as well, those two massive concrete arches. We'll see this characteristic in all of the tension structures we examine in this lecture. The principal load-carrying elements carry load in tension, but these elements always need to have something to react against. And so, while cables and membranes are the stars of this show, we'll typically see compression elements in an important supporting role as well. The bottom line is that you shouldn't interpret the term tension structure to mean that there's no compression anywhere in the associated structural system. There almost always is. Indeed, the only exception to this rule that I can come up with is the simple deck-on-cable suspension bridge configuration that we looked at back in Lecture 8, like this one in Vancouver, which consists solely of tension elements, those long cables, attached directly to the foundations of the structure. Now, the Dorton Arena is an extraordinary structure that inspired many modern architects and engineers. These include Frei Otto, a German architect whom we'll meet later, and the great Eero Saarinen, who collaborated with Fred Severud on several important structures, including the St. Louis Gateway Arch and the subject that we're going to deal with next, and that's the David S. Ingles hockey ring at Yale University, built in 1958. Begun the year after the Dorton Arena was completed, the Ingles hockey rink has a completely different physical appearance, but it actually uses a very similar structural concept. That gracefully curved central spine running down the center of the roof is actually a reinforced concrete arch, nearly 300 feet long. Steel cables are then strung from the top of this arch outward in both directions, and they're anchored at the top of the building's curved walls. The inward pull of these cables is counterbalanced by the curved walls, acting very much like arches turned sideways. The steel cables then support a timber roof, and it's actually the weight of that roof that gives the cables their curved shape. The overall shape of this structure has earned it the nickname the Yale Whale. Now, at this point, having seen Severud's Cow Palace, Saarinen's Yale Whale, and Nervi's Our Lady of Maytag, I must respectfully request that we please stop this nonsense. These are, after all, great structures. They're entitled to just a bit more respect than they've been getting. Thank you. While we're on the subject of oddly named buildings, let's turn to Fred Severud's other great structural design, Madison Square Garden in New York City, constructed in 1968. Madison Square Garden is a major sporting arena, cylindrical in shape, and located on 7th Avenue between 31st and 33rd Streets in New York City. Which is to say, Madison Square Garden is not a garden, it's not square, and it's not located at Madison Square. This building is actually the fourth New York building named Madison Square Garden. The first two were, in fact, located at Madison Square, and the second one did have a garden on its roof. When the third one was built at its new location, the name was retained. But what really concerns us here is not the building's name, but its structural system. The cylindrical outer shell, 425 feet in diameter, is a relatively conventional steel frame structure with precast concrete exterior walls, as you can see in this photo where the steel frame is still under construction. But there's nothing conventional about the roof of this building. It is a wonderful example of a tension structure called a hanging dish. Let's explore this configuration by building a model. Here you see a representation of the outer walls of Madison Square Garden. You see a ring located around the entire circumference of the building at the top of the structural columns. Down below we have another ring which is currently sitting on the floor of the arena, but we're going to raise it up by actually suspending it from a series of cables. And as you can see in my model, I'm using chains for these cables in the model, just as I use chains for the various suspension bridge models that we've put together earlier in the course. The actual cables in Madison Square Garden were steel cables, not chains, but I like to use chains because they are a little bit more visible, because they drape a little bit more nicely, and because they very clearly accentuate the fact that these elements are incapable of carrying any compression whatsoever. They are true tension structures. And so here we have the basic structural system of Madison Square Garden. Now, the actual building used far more cables than this. I've only used 6 here for the sake of simplicity so you can understand the system without too much clutter. But this is how the system works. Of course, we need a roof over the building, and the roof was created by simply using precast concrete panels, which were then put in place on top of the cables and used to support the roof loads that were applied to the top of the building. This overall structural system is a thing of beauty because it demonstrates equilibrium in action. The cables, of course, are in tension. The cables are all pulling outward on this central ring, so they're placing the inner ring entirely in tension as they try to expand it outward. At the same time, the tension in those cables is pulling inward on the outer ring, and so the outer ring is actually called a compression ring. And as a result, the entire system is in balance. It's in equilibrium. There is no net outward thrust or inward pull transmitted by the roof system to the structural system below the roof. The only load that's transmitted from this roof system down into the structural frame and down into the foundation is the weight of the roof and the weight of any load that's applied on top of it. Here you can see Madison Square Garden under construction, with those draped cables up above on the top of the photo. And here's the completed structure viewed from essentially the same vantage point. Note that from an architectural perspective, the draped cables tend to focus attention at the center of the arena, an added advantage of this configuration. Perhaps the most fascinating aspect of this hanging dish system is that it's the direct opposite of a dome from a structural engineering perspective in three significant ways. First, each of those draped cables in the hanging dish takes the shape of a catenary. Flip it around and you have the optimum shape of a dome. Remember Robert Hooke and the dome of St. Paul's Cathedral. Second, the lateral restraint around the base of the hanging dish is a compression ring. The lateral restraint around the base of a dome is usually provided with a tension ring. Remember Filippo Brunelleschi's chains around the base of his dome in Florence. And finally, that central element in the middle of the hanging dish is a tension ring, while a dome uses a compression ring in the center. Remember the oculus of the Pantheon. The associations between these two forms really are amazing, and as a result, each helps us gain a deeper understanding of the other. Now, in 1968, the roof of Madison Square Garden was regarded as an innovative structure. Nonetheless, in terms of load carrying, the hanging dish is essentially identical to the ancient velarium, that rope and canvas awning over the Colosseum in Rome. We know about the velarium from several ancient sources. And while we don't know exactly how it was configured, most modern reconstructions look more or less like what you see here. Ropes were anchored out on the ground outside the perimeter of the Colosseum, and then they were run up over the tops of 240 wooden masts that were mounted in sockets around the cornice on the top level of the building. And then they were draped out across the arena, just like those cables at Madison Square Garden, and probably attached to a tension ring in the center. This web of radial lines supported cloth awning panels, which could be deployed or retracted with additional ropes and pulleys. Ancient sources tell us that sailors from the nearby port of Ostia were employed for this task. And so, just as the velarium protected ancient Romans from the hot Mediterranean sun as they enjoyed the carnage of the day, so the garden's suspended dish roof protects today's fans of sport and spectacle as they enjoy the modern equivalent of gladiatorial combat. But how does a dish-shaped roof drain away all that rain and snow that falls on the roof surface? Well, a variety of different solutions have been used in various different implementations of this basic structural concept. Some early dish roofs of this type used interior drain pipes that ran from the base of that tension ring back out to the perimeter of the building. But this arrangement was unsatisfactory to most architects because the drain pipes cluttered up the appearance of the interior space. Other buildings used pumps to remove accumulated water from the roof without using unsightly interior drains. But Madison Square Garden uses a far more effective scheme. As you can see in this photo, a circular one-story structure has actually been constructed on top of the cable-supported roof. This structure houses the ventilation, air conditioning, and central lighting systems for the building. Its roof is sloped slightly outward so that water falling on it runs out toward the perimeter of the building where it's collected and drained out. Madison Square Garden is an important engineering landmark. Sadly, its structural innovations were gained at a very high cost. Back in the mid-1960s, an existing building had to be demolished to make room for the garden. That building was Penn Station, the magnificent Beaux-Arts structure designed by McKim, Mead & White and modeled on the Roman baths of Caracalla. There's only one consolation for this irreplaceable loss. Public outcry over the destruction of Penn Station provoked the creation of the New York City Landmarks Preservation Commission, which has since saved several important structures that otherwise would have fallen to the wrecking ball, just as Penn Station did. But I digress. A fascinating variation on the hanging dish roof can be found in the Utica Memorial Auditorium in upstate New York. This building was actually constructed 9 years before Madison Square Garden, but it actually adds another level of structural sophistication, which is why I'm discussing it after the garden. Well, you know what comes next. Let's build a model. Or perhaps more precisely, let's modify a model, because in this case, we can start with Madison Square Garden and work from there. What we're going to do to convert our structural model of Madison Square Garden into a model of the Utica Auditorium is to add another ring to the top of the existing tension ring. So here we'll add the ring, and we will plug it into the tension ring below. And what you can see is we have a series of cables already attached to that second tension ring. And as you can probably guess, we're going to take those cables and run them out to the perimeter of the building. I'll start with the first two to get us started. And now let me very quickly continue attaching the remainder of those cables. That completes the installation of our second set of cables, but we're not quite done building the Utica Auditorium roof yet. In order to ensure that the cables are drawn tight so that they properly drain, we're going to add a few vertical struts that separate those two cables in each case. So I'll go ahead and add the rest of the struts at this time. That completes our structural system, or at least our simplified representation of the structural system of the Utica Auditorium roof. And what is it? Well, fundamentally, it's a giant bicycle wheel. In practice, it works just like a hanging dish, except through the addition of that second set of cables, we now have our roof positioned on top of the cables, sloping outward, so this roof drains normally without any sort of additions or drainage mechanisms that we had to have with our dish roof. More importantly, this roof structure is actually significantly stiffer than the simple hanging dish arrangement. And so it's much less susceptible to problems with wind-related vibrations. It's really an incredibly clever structural system. So why was the Municipal Auditorium in Utica, New York, the subject of such an important structural innovation? Well, it turns out that the quality of the soil on the project site was quite poor, meaning that its load-carrying capacity was relatively low. To ensure that the building didn't overload the soil, it had to be very light. The cable-supported roof was a direct response to this situation, a wonderful example of constraint as a stimulus for innovation. This photo shows the roof under construction, and as you can see, it is very light indeed. Now let's look at one final variation on this same theme. This one's called a cable dome, and it may be the most counterintuitive structure you'll ever encounter. A dome made almost entirely of tension elements. The world's first cable dome was the 390-foot diameter gymnastics hall, invented by David H. Geiger for the 1988 Olympics in Seoul, Korea. Here it is, but again, this photo doesn't really depict this fascinating structural system very clearly. So let's build a model. As you see, I've already done some work preparing the model for construction. We're starting with the same basic structural arrangement as both Madison Square Garden and the Utica Memorial Auditorium, and we're also starting with a series of draped cables intersecting at the center and attached to a tension ring. But now each segment of the cable has two short struts attached to it, and those struts have a single diagonal tying the bottom of the strut back to the main cable. In order to put the dome together, I'm going to start by connecting this series of cables which are draped down from the bottom of the tension ring back up to the main cable. And in doing so, I would ask you to note that as I attach these cables, that tension ring actually begins to lift upward. And indeed, this is one of the critical characteristics of the cable dome, that as it is assembled, it actually raises itself up without the aid of any additional temporary formwork or shoring. That's the first step in the creation of the cable dome. Now the next step will be to connect together the bottoms of those struts. Now, We could create something very similar to the Utica auditorium roof by simply adding a tension tie from the bottom of each of these compression struts across the dome. However, what David Geiger saw was that there was a much more interesting way to accomplish the same thing. Rather than establishing a tension tie directly across the bottom of the dome, he realized he could get the same effect by adding a circumferential cable that goes around the circle instead of across the circle. So I'm going to attempt to replicate that tension connection. We're going to have to do two of them, so I'll start with the innermost circumferential ring of the cable dome. And now that circumferential ring is almost complete, but I need to make one last connection. And again, watch that as I make the connection, as that circumferential ring is drawn tight, the cable dome itself lifts up in the center. That was the first of two circumferential rings. Now let's do the second. And now we'll make the very last connection. And there you have it, the Geiger cable dome. Notice that the structural system is similar in concept to the bicycle wheel at Utica, except the function that was previously performed by that bottom radial cable is now performed by these circumferential rings. So really, this structural system only makes sense when you view it from 3 dimensions. The cable dome is an ingenious structural system that exploits a concept called tensegrity, which was first proposed by Buckminster Fuller, the inventor of the geodesic dome. Tensegrity has been the basis for some really interesting modern sculpture, like the work of Kenneth Snelson, shown here. A tensegrity sculpture is an arrangement of very slender tension members, wires or cables, and a smaller number of compression struts, with no two compression struts ever touching each other. Buckminster Fuller called these struts small islands of compression in a sea of tension. What makes tensegrity work is that there have to be at least 3 tension members connected to the end of each compression strut. These 3 tension forces then keep the end of the strut fixed in its position in space, and if both ends of every strut are fixed in this way, then the entire framework becomes rigid. Geiger's tension dome follows this same principle, as you can see if you look very carefully in this photo. But in practice, it's a bit easier to see it on our model. If we go to the model and we focus in on, say, this particular compression strut, if we look at the top of the strut, we'll see 1, 2, 3 connected tension elements. At the bottom of the strut, once again, 1, 2, 3 tension elements. The net result being the entire structural system is stable and indeed quite stiff and quite capable of carrying significant load. And so we see that this cable dome does in fact follow the principle of tensegrity. Kenneth Snelson's tensegrity sculptures are fascinating works of art, but in my view, David Geiger's tension dome is far more impressive because it integrates this intriguing geometric form into a functional structural system. Landmark cable roof structures like the Dorton Arena, Utica Auditorium, and Madison Square Garden all used steel or concrete roof decks. But as early as the 1950s, a few engineers and architects began experimenting with replacing these rigid decks with flexible fabric membranes to create tension structures of even greater efficiency. In 1951, a young German architecture student named Frei Otto visited Fred Severud's design office while Severud was working on the Dorton Arena project in North Carolina. Inspired by what he saw, Otto returned to Germany and began designing cable net and membrane structures. He experienced great success and is still considered to be one of the world's authorities on membrane structures. The greatest challenge in designing membrane structures is defining their geometry. Otto met this challenge by using physical models to create natural shapes, shapes that couldn't possibly have been defined mathematically. And then he replicated these shapes in steel and fabric. Otto's models were made of chain, string, netting, plastic sheets, even soap bubbles in some cases. This so-called form-finding method is reminiscent of Gaudi's technique for the design of La Sagrada Familia, as we discussed back in Lecture 8. And it has produced similarly unique structures, like the 1972 Olympia Park in Munich, a series of cable-reinforced polyester fabric membranes stretched between cable-stayed columns. If you visit this structure and are particularly adventurous, you can actually take a roof climb over the Olympic Stadium and experience those amazing forms up close and personal. Since the 1980s, high-powered computer models have allowed engineers and architects to accomplish this same end computationally, but Otto's natural forms still serve as the inspiration for many modern tension structures, like the Denver International Airport, with its glistening white membrane roof resembling the nearby snow-capped peaks of the Rocky Mountains. In these undulating peaks, we can actually see a hint of the great suspension bridges, which are, in essence, tension structures as well. During this lecture, we've looked at just a few noteworthy examples from the wonderful world of tension structures in buildings. I hope they've given you a sense of the beauty, efficiency, and nearly infinite variety that characterize this structural form. In all of these examples, we've seen that tension structures generally are not composed exclusively of tension members. They invariably include a few isolated compression elements as well. And in a sense, it's these compression elements that make tension structures so interesting. It's at the interfaces between cables and the compression ring of Madison Square Garden's hanging dish, between cables and the vertical struts of the Utica bicycle wheel roof, between cables and the concrete arches of the Dorton Arena. It's at these connections where we can see the principle of equilibrium playing out so vividly. And because the cables differ so visibly from the compression elements in these structures, we can clearly see how their internal forces counterbalance each other, how they interact to make the structural system work. And there's a special joy to seeing and understanding structure in these systems. Thank you.